Hey everyone, Dave here. This is lecture 4, of course. I'll just bring it up. And this one's on covalent bonding, and we'll start having a bit of a think about molecular shape as well. Again, skip the lecture objectives. You guys look at them later. Okay. Now, if you recall, in the previous lecture, we looked at ionic bonding. And the idea there was that we had a metal reacting with a non-metal. And it's kind of a marriage made in heaven. The metal wants to get rid of an electron, the non-metal wants to pick one up. And of course, what you get at the end of that are two ions. One, of course, is a cation, the other one's an anion. And the two oppositely charged ions attract one another and form that crystalline lattice structure I was talking about in the last lecture. Now, there is another way of satisfying an atom's lust to be get an electron configuration like a noble gas, and whilst it's probably not quite as satisfying as forming ionic compounds, it nevertheless does work for non-metals. So this is an example of where two non-metals actually combine, and the bonds that form between them aren't ionic bonds. That is, they're not attractions between two oppositely charged particles, but it's because they're actually sharing electrons. When atoms combine and form these particular types of compounds, they're referred to as molecules. Okay, now I've already brought this idea up that in this case, instead of this give and take arrangement that I was talking about with ionic compounds, this is all about sharing electrons. So how does it work? Well, here's an example here. Fluorine, there's my arrow, right. Fluorine here, if we look at this fluorine atom and this fluorine atom, they can form this molecule, F2. How does it work? Well, they're still driven by a need to get a noble gas electron configuration. If we just look at this fluorine here with its electrons, if you recall, fluorine's got a 2p5 electron configuration in the outermost shell. A 2s2 2p5 electron configuration in the outermost shell, making a total of 7 electrons. You count them up here, we've got 2, 4, 6, 7 electrons. Of course, these two guys here, they're in the inner shell, principal quantum number 1. There's your 1s2 lot. So here, really, our 7 electrons are represented here. That's our 2s2, 2p5 electrons. Alright, so we've got 7 there. Now you all know, of course, that a fluorine atom will try to pick up an electron to look like its nearest neighbor noble gas. In this case, it's neon. And if I look at this fluorine atom here, of course, it's exactly the same. They're just designated differently here so I can distinguish between them. But again, you've got 2, 4, 6, 7 electrons. It wants to pick up one as well. Now in this case, because there's no metal around that can give an electron, what can happen instead is that these guys hook up and share. Now if you look at this, whoops, sorry about that, let me just go back here a sec. Let me get my trusty pen out, my felt tip pen. If you look at this atom here, as it's drawn at the moment, if you count this electron here, this blue one from the other atom, it's actually got 2, 4, 6, 8. In other words, it does have an electron configuration like neon. If you look at this atom here, it's got 2, 4, 6, 8. It's got an electron configuration like neon. Now, it's not perfect. I'm sure fluorine would be much happier if it reacted with a metal and could pick up an electron and hold all by itself. But at least for part of the time, they're looking like a noble gas electron configuration. And that's essentially the whole rationale behind covalent compounds. They mightn't get exactly what they want, but sharing is better than not having anything at all. That's basically the rationale. Okay, there's just a little summary for you. Let's look at another example. Oh, and by the way, this will illustrate something else as well. Here we've got two hydrogen atoms. Now, we've designated them a little bit differently. I haven't drawn a circle thing like this to indicate them. Now I've just put a dot there. I've gotten rid of the circle. Now, anytime you write an elemental symbol like this and put a dot next to it indicating the electrons that you're interested in, it's called a Lewis dot structure. And in fact, I think I referred to it back here. Lewis dot structure or Lewis diagram, same thing. Okay, so if we go back here to these two hydrogen atoms, this is an example where we've got a Lewis diagram essentially. This hydrogen's got one electron, this one's got one electron, and they combine here. And now we've got this configuration, and you can see it's kind of like before with the fluorine. There's that hydrogen. From its perspective, it's happy. It's got two electrons. Nearest neighbor, noble gas configuration corresponding to helium, which is 1s2. This hydrogen here is more or less happy. The same reason. Okay? Now, this kind of sharing arrangement occurs with not only elements, two atoms that are the same element, like hydrogen and hydrogen or chlorine and chlorine, but also with any non-metal element and any other non-metal element. So let's have a look at this one. First of all, we've got to get our heads around what this sharing arrangement's going to look like, what's in it for each of the respective elements. For fluorine, of course, its main interest is picking up one electron to look like neon. And for sulfur, it's here, it's 2 steps away from argon in the periodic table. There it is. So it wants to pick up 2 electrons to look like argon. So the sharing arrangement's got to be different here. Somehow sulfur's got to be happy getting those 2. Fluorine's got to be happy kind of getting that 1. The way they do it's like this. So here we've got a sulfur atom and 2 fluorine atoms. So when the sulfur's sharing 1 electron here from the fluorine and another electron here from the fluorine, it's essentially the same as it picking up 2, whereas each of these fluorines is picking up 1 of the electrons from the sulfur. The other thing that can happen is that you can have 2 atoms of the same element, but they actually form multiple covalent bonds. So there's a multiple sharing arrangement. So here's an example here with oxygen. Obviously, oxygen wants to pick up 2 electrons to look like its nearest neighbor, noble gas, which is neon. You look at this. There it goes. There's our 2 electrons. If you look up here, we've got oxygen here. There's our 1s2. And this will be our 2s2, 2p4. So it should have 6 here. 1, 2, 3, 4, 5, 6. So these brown ones here, there's 6 of them. If you look at this oxygen atom here, there's 1, 2, 3, 4, 5, 6. So oxygen's got to pick up 2. What does it do? Well, this oxygen shares its 2 electrons with the other oxygen, and this oxygen shares its 2 here. So now if you count up all of them in total, we've got 1, 2, 3, 4, 5, 6, and then the 2 that it shared with this guy, 7, 8. So it's got that 2p6 electron configuration. That is the noble gas configuration. This oxygen's obvious, the other oxygen's obviously the same. But you haven't already become apparent to you the way in which you can represent this kind of bond here, this sharing arrangement, is that for every 2 electrons, you write a single line. Let me just go back here. It's probably not the best example. Here will do. With this hydrogen, rather than writing it as H dot dot H, I can just simply write it as H. Like that. There we go. But that line there actually represents 2 electrons like that are being shared. So if we go back to oxygen again, here, right, it's sharing 2 pairs of electrons there and there, so you'd write it like this. But wait, there's more. You can also not only have double covalent bonds, but triple covalent bonds. So a classic example of this is nitrogen. So here we've got a nitrogen atom, and we've got a Lewis dot structure going on here. So we've got these 3 electrons, and we want to pair them up. Electrons hate being by themselves. They love to be paired up. So we move the dots around, if you like. In fact, I should have put 2 dots here and here for these guys. Probably would have made it a bit less confusing. Alright, so let's see how we go then with this nitrogen. We can see how many electrons are there. We've got 2, 4, 6, 8. And from this nitrogen's perspective, this one here, we've got 2, 4, 6, 8. So again, they've got that noble gas electron configuration. Here's some other examples. You can see how you can start building up quite complex molecules using covalent bonds. We've already visited the hydrogen. There's our 2 electrons there being shared. We've got oxygen there with our 2 pairs of electrons. We've got water. Water is, of course, a combination of oxygen and hydrogen, both of which are non-metals. So we've got 2 shared there and there. And for this one, this is methane. We've got them shared there, obviously there, and there. Alright, I'm going to leave that there and I'll get on to part 2 in a minute.